Thank you for having me. Thank you to Erie Day of Code for inviting me to come and speak today. I've been a long time attendee of the Erie Day of Code, but I've never taken the leap to presenting before, so here's hoping. So when Matt first asked me what the title of my talk was going to be, I immediately fired off IoT sensing in the real world. And then I fired off a description to follow it 30 seconds later, dealing with the trials and tribulations of building an industrial IoT product. And I'm super enthused about telling you about that, but I recognize it may not be applicable to everyone. So I also want to talk about something else, which I think is maybe even more relevant to the people in the room today, which is sort of a way that I think that the Erie development community, the designers, the programmers who are in this room today, can really be part of the revitalization of our region economically. And we may fight with the projector. I don't know. The adapter seems to be on the fritz. But basically, the first part of the talk is going to be a case study about work with a local client in the industrial space and an IoT product that we're building together and some of the details about that. And then I'll also talk about the larger community and sort of some of the opportunities that I see from where I am and that I hope the rest of our community will join me in pursuing. Can I get the slide? There we go. Okay, so I think a lot of us know that Erie's manufacturing past, the legacy manufacturers that we have, like for example in the plastics industry or in the steel industry, that in the future they're going to have to modernize. They're going to have to implement advanced manufacturing techniques in one way or another. And there are a lot of manufacturers in Erie today who are making big investments. But I think there's also a possibility that we make a mistake when we think of advanced manufacturing as being robots and lasers and carbon nanotubes, because the truth is there are a lot of manufacturers in this region and of course all over the country who might not be either in terms of capital investment or in terms of their workforce or in 100 other ways, they may not be ready to make the leap to full automation, full data-driven everything, but we can still make really significant progress and there's a lot of low-hanging fruit. So, and besides, there's no guarantee that today, if a manufacturer in the steel industry goes out and buys a brand new furnace to melt steel, there's no guarantee that that furnace is actually going to be better than the one that they already have, because the other unfortunate reality is that for many industries in America, it's actually difficult to replace the aging machines. They're not made anymore in this country, and you can't have them delivered from abroad necessarily. So there is a real need to address the opportunities and the gap in productivity that develops in legacy manufacturing. And I think that this community and this crowd here today are really in a great position to help with that. So let me tell you a little bit about my client, PSNergy. So PSNergy is an interesting case because they actually come out of the plastics business. They use some plastic injection molding technologies to develop a product, but their product isn't made of plastic. It's made of an advanced ceramic material. And essentially what they do with these radiant inserts, they're called, is they place them inside the exhaust throat of an industrial furnace. This is a furnace that might be melting steel or doing some heat treating or something like that. And they stack these inserts inside of what would you think of as like the chimney of the furnace. And what the devices do is they act as kind of a mirror to the heat. They reflect the heat back down into the furnace so that it doesn't escape through the smokestack. And essentially they can reduce the amount of energy needed to melt or process steel or other materials. And they do it right here in Erie, Pennsylvania, but yet the business has evolved even beyond that. So this is a photograph of a red-hot radiant tube insert glowing inside of a steel furnace. And this little insert, which is made of these advanced materials, can reflect between 9 and 22% of the heat of the furnace back into the steel load that's inside. And what this means is that they're saving 9 to 22% of the fuel that they're burning. So the production of steel 1 ton of steel produces about 117 pounds of carbon dioxide into the atmosphere. And when I first met with PSNergy as a client and I sat down in Carl's office, the CEO, and he started telling me about the company, it was fine. I was excited about the project. But when he started telling me about the emissions improvements that they can make in the production of steel, I really got very interested because it's pretty amazing. So as I said, in the production of a single ton of steel, you're going to release about 117 pounds of CO2 into the atmosphere. But these radiant tube inserts, saving between 9 and 22%, that's 10 to 15 pounds of CO2 that doesn't reach the atmosphere for every single ton of steel produced. So that sounds pretty good, but you have to understand the scale of steel production and what a real large steel furnace actually consumes. So on the largest steel furnaces, there might be 500 of these burners. And in a single hour, they're putting into the atmosphere 25,000 pounds of CO2. Okay, so over the course of a year, these inserts could remove 88 million pounds of CO2 that would never be released into the atmosphere, and that's from one steel plant. So just this technology alone is transformative in terms of business. It makes the process faster, it makes the process cheaper, it makes the businesses more competitive with overseas rivals and others, and it also is making a huge impact in an issue that is certainly near and dear to my heart. But there's actually even another larger innovation that you can make with steel and with furnaces. And I'll tell you about that next. Just so you get a sense of what we're talking about, this is a steel furnace here. This is a small one. Each of those black tubes at the top is what you would think of as the exhaust stack. So this is probably about 24 burners on this side and 24 on the other side. So a large steel furnace would be like this one, except stacked 10 of them on top of each other, over 100 feet high. And inside of a furnace like that, you might have a mile of molten steel moving all the time, constantly. So those are very, very large processes, very, very energy intensive. So the second energy-saving innovation that PSNergy came up with was tuning the combustion process. So it turns out that inside of a burner, inside of a furnace, you have to combine the fuel and the air, right? You take the oxygen, you take the natural gas, you burn them, you make heat. But it turns out that if you put in too much air into that process, you're going to blow some of the heat right out the chimney without even using it. And if you don't have enough air, then you're going to be wasting natural gas and you're going to be filling the furnace with soot and grime and all sorts of impurities. And of course, you're wasting gas. So it turns out that there's a pretty narrow range in which you can optimally produce heat in this kind of reaction. And that's measured by looking at the gas that's left over when you've finished burning. You want to look at how much oxygen is still in the flue gas after the burn is complete. It should be about 2 to 5%, somewhere in that range. And so if you see a furnace is blowing 10%, that means that you're blowing too much air into the furnace. And if you see that it's burning 0, then that means you're actually wasting fuel. You're probably throwing natural gas right at the smokestack. So again, it's important to dial this in as closely as possible. But PSNergy had a solution to this problem, and they have for years. They send a person to each of their clients, which are the steel plants, and they plug a little handheld meter into the tube. And they watch the oxygen level, and then they turn a wrench to adjust the airflow until they get it dialed in. But they noticed that even just walking away and coming back a week later, the furnace was no longer in tune. So there needed to be a way to monitor this information in real time in order to continuously make adjustments, because there's lots of variables that we can't control. So this is where I started to get involved in the project. So I may have blown right through this slide. So the other thing to recognize is that no one, as far as we know ever, had actually looked at what was happening inside of a steel furnace in any great detail, not for longer than a few minutes at a time. Because, of course, the human element is that these furnaces are very hot, 150 degrees easy standing next to one, and you can't stay there for very long, even just from a health perspective. So you have to be able to, get in, get the work done, and get out. And that's especially true on the large ones. You can imagine that it's just a hellish environment. So to continually monitor this was going to require a solution that was going to be automated or somehow, remote. And so then this is where I started to get involved in the project more. But in the end, we ended up building a small metal case about the size of a PC tower. And we pushed a bunch of pumps and sensors and thermocouples and pressure transducers and motors into this case. And we were able to deploy that into the steel furnaces and monitor that information continuously, which means that now we don't have to send someone on an airplane to go and tune a furnace across the country. We can do it from here by talking their technicians through the changes they need to make while we monitor in real time what's happening on the furnace. So inside of that box, we have motor control boards, we have all the sensors I mentioned, we have a whole bunch of electronics, and at the heart of it all is a Raspberry Pi. If you're not familiar with the Raspberry Pi, it's an amazing little machine. It's a single board computer, costs about $30 to buy. It has a quad-core processor. It has 1 gigabyte of RAM. They just announced a new version that's going to have 4 gigabytes of RAM. It's got HDMI ports. It's got a graphics accelerator. It has an amazing amount of power for a computer that's about the size of a credit card, a little larger. And it's the brain of everything else that's inside that box. And so mostly what I did was to develop the software element that ran on that Raspberry Pi. And I'll talk about that in some more detail. Here's a picture of the inside of the case that we ended up building. You can see those are the pumps. These are 4 pumps here that draw air from the furnace and analyze it. There's motors underneath of that to drive the pumps. You have some sensors and some plumbing and whatnot, but underneath of this board right here is where the Raspberry Pi lives. And this has been the product of a lot of work. We started off with a box that had an awful lot of wires in it. And over time, we learned that wires can come loose and soldering can be imperfect. And so we started having all the wiring replaced with custom printed circuit boards. Now everything mounts securely onto a couple of different boards. We've got a whole bunch of off-the-shelf components sort of all printed onto one circuit so that we don't have to have a whole bunch of little dongles and adapters and things. But before I get into any more of what I built for the Raspberry Pi, I should probably explain how I got here. So I come, I think, in many cases, in a similar path to many of you. I started off in web design and web pages back in the late 90s when I was still wee. And then I moved into content management systems and I worked on Joomla. Hold your applause till the end for Joomla, please. I did some work on Joomla back in the last decade. And then eventually I discovered Laravel and Yi, and I started building web applications with PHP and then eventually REST APIs. But at some point along the line, I learned about the Pi, and I bought one for home, and I put it on the back of my TV, as so many people do. And I don't know what inspired me to do it, but I decided to put a little blurb on my website at the time that, by the way, I also can do things with the Raspberry Pi. And that website did very little for me, but I did get one lead, and it was for a Raspberry Pi project. And it actually turned out to be in the casino industry in the Caribbean, of all things, putting Raspberry Pis in the back of slot machines and using the Pi to digest the data that was streaming through the casino and figure out how to improve the operations and reduce costs and all that stuff. So that was a fun project, but it's always really nice when your personal passion and your personal values also align with a project. And the casino industry, while it was, it was a great project and I really got a lot out of it, it was less aligned with my values than something like saving energy. So it's been great to have more opportunities to work with the Pi. But over that time, I sort of got familiar with the Pi and came up with some ideas that didn't work so well, and then folded the learning from that into later projects. And so now I feel like I'm pretty good at working with the Raspberry Pi as a commercial device. So if you think about what a Raspberry Pi is like from the perspective of a web developer, which is, after all, is how I come into it, right? I come into this not from the perspective of someone who writes a lot of C code, not from the perspective of someone who's like really a hardware hacker or is interested in like motors and you know, gears and things like that. I was much more of a classic, you know, like application development guy. So looking at the Pi from my perspective, I saw something that was essentially a web browser. It was essentially a client on, you know, in any other context. Maybe a not such a powerful client, but you know, not really different fundamentally from the server-client paradigm that I was used to thinking about. And so when I came to the Raspberry Pi, I was thinking way more in terms of like HTTP back and forth, and not in terms of sockets or anything, you know, sort of low-level serial communication and things like that. My feeling about the Pi was that, and maybe this is just because I'm getting a little older now, a quad-core processor, all that RAM, I mean, we got to be able to do something with this machine. So it's got a lot of power in it. So I really felt like the Pi could be relied upon to run its own services, to run Redis, to run a PHP engine if you needed to, or even a web server if, God forbid, you should choose to do such a thing. So to me, it was just another Linux command line, which I was used to from 100 other projects. So I did have some concerns, though, like not really sure about serial communications. I mean, I know how to open a serial port. I can certainly find examples online, but don't ask me to shift the bits 3 steps to the left and do an XOR. And I've never been that programmer. That's never been my strong suit. So I was really worried about that. And it turns out that I needn't have been worried, because there's a whole lot of high-level languages you can run on a Linux command line, things like Node and Python, and pretty much everything that we talked about at the conference today, you could probably run on a Raspberry Pi if you so chose. So I was able to find tools that I was already familiar with, assemble them in ways that felt to me like they were sort of the right way to do it from a future-proofing perspective, and keep my head, for the large part, out of the weeds of individual, you know, let me write a protocol to move a piece of information across a wire. You know, I felt like if I got down into that I was seriously reinventing the wheel. So here's the slide where I talk about the technologies that I ended up deploying for this project. I have a bunch of little microservices written in Python and in Node.js. They're run by PM2 on the Raspberry Pi. I use Redis for everything. I use CouchDB to persist configuration changes across a wide dispersed network of Pis. Most of the real-time data goes into Influx. And for a free, cheap, easy solution for looking at all this beautiful data, we use Grafana. There are so many wonderful things about this stack. I can't even begin to tell you. But I think the very best part of all of it is Redis. If you're not familiar with Redis, it's like, it looks like a server. You know, you can connect to it on a TCP port. It has its little protocol, its little commands. But it's really an extremely highly optimized memory store. A memory store that you can talk to from Node, that you can talk to from Python, that you can talk to from any language you can think of. And it allows you to achieve a level of inter-process communication that otherwise would be tedious to do. So like, you can maintain a consistent data set between 3 or 4 different processes using Redis. And we also are now using the newest features of Redis, which include consumer streams. If you're familiar with Kafka, they have things like that. It's real-time messaging, pub sub, stuff like that. So there's a lot of capability there, and it's been enormously helpful. And I just looked at one of our Pis that's in production right now, and the instantaneous amount of data that it's processing every second through Redis, enormous, gigabytes and gigabytes. But the amount of memory that it's using, 2.7 megabytes. You can't beat that. So, yeah, I really feel like the Raspberry Pi is extremely capable, and you can rely on it to do a lot of things. And you might as well be using at least 1 or 2 of those cores while you're at it. So in addition to just gathering data out of a sensor, I'm also trying to do some processing of that data, maybe a little bit of machine learning on that data, identify some patterns or some trends, because why not? We have these powerful devices that are at our fingertips now. So yeah, I think this stack has worked out pretty well. There are some things I would do differently. But I think the number one lesson I would warn you about, or the number one thing I would like you to know going into a project, if maybe you've never done a project with hardware before, is that you will prove Murphy's Law by exhaustion. Every single thing that can go wrong will go wrong in ways you never thought would happen. Because there's a little bit of an adjustment when you're a software developer and you're used to writing code, and the code always works pretty much the same way. You know, it always goes from line 1 to line 2 to line 3, and pretty much everything you do is instantaneous. And there's only so many different ways. If you don't have a bug in the code, it probably will perform the way you expect. But once you get into the real world, now you have all kinds of X factors that you couldn't have predicted. And so I definitely had to be patient along the way with myself and my partners at PSNergy with me as well, because we do find little glitches in the hardware and little glitches in the sensors. And I think, you know, sort of before you embark on a project like this, it's important to understand that every sensor that's made, whether it's an accelerometer to measure, you know, direction, or if it's a thermocouple to measure temperature, or a pressure transducer, or whatever, all of these sensors, they're based on physics. And physics is a tricky thing. A lot of these sensors have little caveats that you might not know about until you push them to their limits. So for example, if you're reading a sensor once every second, you may see exactly what you expect. The temperature of the room is 76 degrees, 76 degrees, 77 degrees. But if you're reading it 10 times a second, you may occasionally get negative 50 thrown in there. And that's the kind of thing that can happen, and your code has to be resilient to that. So it's important to plan in advance for as much of that as possible. So in terms of some practical advice, we had to just assume it was going to be offline all the time, or most of the time. Because once you get inside of a real industrial environment, the internet is not so good. Whether it's the cellular modem dropping off, or the guy who drives a forklift, every time he drives it in front of the station, the Wi-Fi goes down. You know, there's things like that happen. So you have to kind of assume and build in from the very beginning that you're not going to have access to the internet. You're probably going to have to store things for a while. We had one outage. We didn't even know the machine was not online. We just weren't paying close enough attention. But it was offline for almost a month. And when that machine came back online again, it filled in millions and millions of data points that it was storing. And that's Redis, by the way. Extremely useful. You also need to design your communications to be as efficient as possible, because when you do get internet back, it might only last for a few minutes. And what you don't want to do is to be sending a 14-digit timestamp with every single piece of data. You got to find ways to reduce that overhead, to compress as much as you can. Find clever ways to spread the sensing around a little bit. There's all sorts of interesting approaches that we came up with to reduce that overhead. And you also have to be aware that most of the providers, there's a million devices out there. I mean, there must be 150 commercial offerings for small IoT devices. But you got to be careful, because a lot of them don't work offline, so they wouldn't work for us. Or they're really about selling you a cloud-based service. And so there's a lot of fees involved, and especially as you get to scale, there's a lot more fees. So we chose to, we host stuff on AWS, but otherwise, you know, we try to use mostly our own systems. And because, especially like with cellular modems, they do charge by the gigabyte, so you have to be careful with that. If you're not a hardware person, find somebody who is and partner with them. Thank goodness I have the electrical engineering help and the mechanical help that I get from PSNergy, because without them, put it this way, when you're trying to figure out if the bug is in your code or in the wiring of the box, it's really hard to tell, you know? So you've got to make sure that that wiring part is nailed down. That way you can find all the mistakes that you've made, or that I've made. Yeah, absolutely important to have good partners. And then finally, this is a tricky one. So when you put a box in the field and you got there on an airplane and you walk away and you go back to the hotel and then the next day you fly home and the pump doesn't work, you have to have some way of diagnosing that. And you can't just ask the pump if it's working or not. We've learned that. But you need to have an independent, totally separate way of interrogating what's really happening on the ground. Things like maybe putting a microphone inside the box or an accelerometer inside the box to detect physical motion. You know, if you're relying on a valve to open, you might want to put a pressure sensor somewhere so that you can tell if the valve opened independently. If you don't, you're just going to have to buy another plane ticket. And you sort of need to think carefully before you begin the coding process. How will I have sanity checking? How will I know if this is working and it's just unusually quiet or if it's broken, right? So having said all the trials and tribulations of what it's like to build a sensing platform, and if anyone has more specific questions, I'm always welcome to come up to me afterwards and I'll discuss it with you more. But one of the things that I think is important about this talk, or why it might be relevant to the Erie Day of Code community, is I think that we all basically want to do good in our community. I think we all basically want to do interesting and impactful work. I think we want to make a difference if we can. And for me personally, it's very important to be wholehearted in whatever work I'm doing. So I want my work to align with my personal values. I want it to align with my economic needs. And I want it to align with my talents and skills, right? And so it can sometimes be challenging to find projects like that. But I really encourage everyone to keep your ear to the ground. You'll find something that will fit that niche for you. So I'm a person who's pretty concerned about climate change, maybe more concerned about climate change than most of the other issues that I am interested in. And I think I've done about all that I can in my own personal life to reduce my own impact, short of totally giving up avocado toast or something crazy. So as a developer, though, I see this opportunity because industry is easily the biggest user of energy. And so many industries need help making small improvements or big improvements, but starting with just the smallest and simplest level. There are so many manufacturers right around us here in this region who need help just determining if a machine is on or off, determining if a valve is open or closed. And every single person in this room, if you have a development background at all, is just as qualified as I was on day one to make those kinds of solutions now that we have hardware like the Raspberry Pi. We have languages like Python and Node. We don't have to learn ladder language. We don't have to learn PLC programming in order to be able to go into an industrial setting and to say, I think I can make that a lot better. So let me ask you if you can do any of these things better. Okay, if anyone in the room would be able to build a database that wasn't a CSV file. Some of you, maybe, hopefully. What about getting some data from point A to point B without using an email attachment? If you can do that, you're making a big contribution. What about a USB thumb drive as a means of moving data from point A to point B? If you can think of any way to improve upon that, then you're making a big impact in this space, because these are real examples, and they're actually some of the higher end, more advanced systems that I've worked with. How about TCP sockets, where every single machine on the factory floor has its own worldwide routable IPv4 address? No encryption needed, right? It's fine. Who could possibly guess the address? How about this? For the people who talk about UX and UI, is there anyone who might be able to do better than having to physically stand in front of the machine and look at a screen to read the number? I think most of us probably could. As a matter of fact, sticking a webcam behind a machine and pointing it at the screen is a huge improvement. Because you're saving a guy having to drive 30 miles every single night to check on a machine from his home. And you're making a big difference in that business. There are so many opportunities out there for simple things. So I think you can help. I don't think that we need to be replacing complicated PLC systems or writing the latest avionics software for fighter jets or anything like that. Leave those things to the folks who are passionate about that very hardcore level of hardware and software programming and assembly and all that stuff. There is other opportunities out there for anyone who wants to try to bend the curve a little bit on energy use. And I think a lot of you in the audience today could be solving these problems or helping to. And the energy efficiency difference that you make for these customers is obviously also translating into things like more profitability, more productivity, faster time to market, more competitiveness, all of those things. And so, yeah, thank you so much. And I don't know how am I on time, Matt? Did I go too fast?
Perfect.
Anyone? Okay, cool. Well, let me share one final anecdote so that I can push it just a little beyond where I should. So this is a super simple example, but PSNergy, when they make their radiant tube inserts, they have to bake them in an oven. Okay, they got to bake them for like 8 hours at a certain temperature, and then they have to cool completely before you can move them. And this oven is huge, industrial oven. And the problem was that by the time the inserts were ready to be removed from the oven, it was like midnight or 2 in the morning and there was nobody there to do it. So what we came up with was we put a little arm on the door and we just pushed the door open at the right time. We only had to crack it open a couple of inches. And that would, by itself, cut 12 hours off of the cycle time to make the product, which is enormous. Their productivity, the ability to make more parts increased dramatically just because we could nudge a door open with a little arm and a Raspberry Pi. So there are these opportunities out there, and I hope that everyone will look for them and consider maybe trying to do these kinds of projects. Keep your ear to the ground. There are these things out there. And if by any chance there's any manufacturers in the room, look around. All these developers around you probably can help you with your problem. So thank you so much.